Welcome back to Vision Vitals, your ultimate source for embedded vision insights. Today's episode explores what makes autonomous vision systems reliable or unpredictable: timing alignment. Modern vision systems are complex. Cameras, LiDAR, radar, and inertial sensors rarely work alone. They feed a shared perception stack held together by precision. In this episode, we focus on why real-time sensor fusion depends so heavily on disciplined time alignment, especially in autonomous applications. Our vision intelligence expert joins us to break down where fusion succeeds, where it struggles, and how product developers approach precision from the ground up.
Glad to be here. This is a topic that sits at the intersection of hardware design, system architecture, and perception reliability, so I'm looking forward to diving in.
To set the stage, how should real-time sensor fusion be understood in autonomous vision systems?
Real-time sensor fusion refers to the process of combining multiple sensor streams so that they describe the same physical moment in the environment. Cameras capture visual frames, LiDAR reports depth returns, radar measures velocity and range, and IMUs describe motion. Fusion works when all of those measurements align temporally and spatially. In NVIDIA Jetson-based systems, fusion often happens close to the edge, where inference, tracking, and planning run continuously. Real-time in this context means the system processes synchronized data fast enough to guide immediate decisions. If one sensor reports data from an earlier or later instant, the fusion output starts losing its precision. So, real-time fusion is less about raw speed and more about temporal consistency. The system needs confidence that all inputs correspond to the same slice of time.
Once multiple sensors feed a shared perception stack, why does timing alignment become central to system behavior?
Timing alignment becomes central because perception algorithms assume coherence. Object detection, depth estimation, and tracking pipelines expect that inputs describe a unified world state. When sensors operate on independent clocks, drift accumulates. Even small offsets create discrepancies where objects appear shifted, stretched, or unstable. For example, a camera frame may capture one moment, while LiDAR captures a different moment milliseconds earlier or later. As vehicle speed or platform motion increases, those timing gaps translate into larger spatial errors. Alignment stops being a secondary concern and becomes a core requirement for predictable behavior.
What kinds of perception issues emerge when camera, LiDAR, radar, and IMU streams drift out of temporal alignment?
Several classes of issues surface. Depth fusion starts breaking down because visual features and range returns fail to overlap correctly. Object bounding boxes wobble or jump as different sensors disagree about position. Tracking pipelines struggle to maintain identity because motion estimates from the IMU fail to line up with visual motion. In some cases, objects briefly disappear or reappear because the fusion layer treats conflicting inputs as uncertainty. Over time, these inconsistencies degrade confidence in the perception output, even when individual sensors perform well on their own.
How does timing drift translate into real-world inference problems such as depth errors, object instability, or tracking loss?
Inference models depend on structured inputs. When timing drifts, the structure breaks. Depth maps become smeared or warped because the system fuses range data from a different instant than the image frame. Object detectors may still fire, but their outputs fluctuate frame to frame. Tracking algorithms then receive unstable inputs and either reinitialize or lose continuity. In motion-heavy environments, these effects compound. What looks acceptable in static tests often collapses under real-world motion.
In NVIDIA Jetson-centric architectures, where does time authority typically reside, and why does centralizing it matter?
In well-architected systems, time authority resides on the compute module itself. The NVIDIA Jetson platform becomes the reference clock that all sensors align to. Centralizing time authority avoids the complexity of reconciling multiple drifting clocks downstream. Instead of correcting offsets after the fact, the system prevents misalignment at the source. This approach simplifies fusion logic and produces cleaner data streams before inference even begins.
How does GNSS disciplined timing using PPS and NMEA establish a shared clock on NVIDIA Jetson Orin NX?
GNSS provides an external time reference anchored to UTC. The pulse per second signal delivers a hardware-level timing edge with very high stability, while NMEA messages provide absolute time context. On NVIDIA Jetson Orin NX, the system disciplines its internal clock using these inputs. PPS aligns the clock edge precisely, and NMEA keeps it anchored to global time. Once disciplined, it distributes this time reference to connected sensors. Cameras, LiDAR, radar, and IMU data all inherit timestamps derived from the same authority, which removes ambiguity during fusion.
What role does PTP over Ethernet play in synchronizing LiDAR and radar data at the transport level?
Precision Time Protocol enables sub-microsecond alignment over Ethernet links. NVIDIA Jetson operates as the grandmaster with reference to the GNSS clock, while LiDAR and radar devices act as subordinates. PTP ensures that packets arriving over Ethernet carry aligned timestamps. That means range and velocity data arrive already synchronized, rather than requiring correction later. This transport-level alignment reduces jitter and supports consistent fusion behavior, especially when multiple high-bandwidth sensors operate simultaneously.
How do PPS-driven camera triggers improve frame determinism for GMSL and MIPI CSI cameras?
PPS-driven triggering aligns camera frame capture to a known time edge. Instead of frames starting based on internal camera oscillators, capture begins on a shared timing signal. For GMSL and MIPI CSI cameras, this produces deterministic frame boundaries. Every frame corresponds to a precise moment on the system clock. That determinism makes downstream fusion cleaner. Visual frames align more reliably with LiDAR sweeps, radar updates, and inertial measurements.
IMUs generate high-rate data streams, right? How does fixed-rate polling combined with disciplined software timestamps keep inertial data aligned with vision inputs?
Yes, IMUs often run at higher frequency. Fixed-rate polling ensures that samples come at predictable intervals. When software timestamps derive from the GNSS disciplined system clock, inertial data aligns accurately with vision frames and range data. This approach avoids irregular sampling gaps and reduces interpolation errors during motion estimation, which helps stabilize tracking and pose estimation.
Now, how should product developers think about sensor fusion timing when architecting autonomous vision systems from day one?
Product developers benefit from treating timing as a foundational design constraint rather than a late-stage optimization. Decisions around clock-based trigger paths and transport protocols shape how well fusion performs later. Starting with hardware-anchored synchronization simplifies perception pipelines and reduces corrective logic. It scales better as sensor counts increase and also brings more precision in real-world matching with the simulations. When timing discipline sits at the core of the architecture, fusion becomes predictable, inference stabilizes, and the system behaves closer to how models expect the world to look.
Before we close, how does Econ Systems' Edge AI Vision Box fit into real-world sensor fusion deployments on NVIDIA Jetson platforms?
Econ Systems has spent over 2 decades working at the intersection of cameras, compute, and system integration. That experience shows in how Darsi Pro, our latest Edge AI Vision Box, is built. Based on NVIDIA Jetson Orin NX and NVIDIA Jetson Orin Nano, this platform brings multi-camera interfaces, hardware-level synchronization, and AI-ready processing into a single unit. For those working on robotics, autonomous mobility, or industrial vision, Darsi Pro removes much of the friction around time alignment. Instead of stitching together external timing hardware and custom sync logic, teams can focus on sensor integration, model training, and edge inference within one cohesive framework. Such consolidation shortens development cycles and keeps fusion behavior predictable as systems move.
And that brings us to the end of today's episode of Vision Vitals. Remember, folks, real-time sensor fusion depends as much on disciplined timing as it does on sensor quality or model performance. Anchoring sensors to a shared precise time and aligning data before fusion begins means that vision systems can hold up under motion and complexity. Thank you for tuning in. We appreciate you spending time with us, and we'll be back soon with more conversations on vision systems and perception design. You can find more details about Darsi Pro on Econ Systems' website. If you need more details on this cutting-edge AI vision box that can empower your teams, please write to camerasolutions@econsystems.com. Once again, thanks for spending your time with Vision Vitals. We'll see you in the next episode.